In this video, I want to talk about the Ohm's law. So before I do that, let's just go over the definition of a resistor. So what do we mean by a resistor, or what do we mean by a resistance? So resistance is the capacity of materials to impede, delay, prevent, or as the name suggests, resist the flow of current or electric charge. So if you remember from before, we used this jagged line to represent a resistor. We can have terminal 1, terminal 2 for the resistor, and we can define a voltage polarity and also a direction, a current direction for this resistor. So resistors, because of their material properties, they resist the flow of current or electric charge. So interaction of moving electrons or like protons and the atomic structure of the material results in conversion of electric energy to thermal energy. Because of this conversion, we say that we have a resistance for this specific material, for example. So now the question becomes, what is the relationship between the voltage across a resistor and the current that goes through it? So that is what is called as the Ohm's law. I briefly mentioned it last time too. So Ohm's law states that the voltage across the resistor, so let's say we have a positive sign here, a negative sign here. So I call this terminal 1, this one is terminal 2. So the voltage across the resistor equals the current through the resistor multiplied by the resistance, the amount of resistance that is measurable. So we have V equal I, the current, multiplied by the amount of resistance for this specific element. So this is a graph that is drawn using the passive sign convention rule. If you remember, we said that if the direction of the current is in the direction of the voltage drop, so we have the positive side here, we have the negative sign here, that means that from terminal 1 to terminal 2 the voltage drops. So if we have the direction of the current be in the direction of the voltage drop, for any equation that we have, we use a positive sign for that specific equation. So if we want to write the Ohm's law for this specific configuration, V equals positive I multiplied by R. Again, this doesn't say anything about the specific values of these variables that we have in the equation. It only talks about the sign of the equation itself. So what about if we have the current going through the opposite direction of the voltage drop? So we have terminal 1 here, terminal 2 here, and again following the passive sign convention, if the current goes opposite the direction of the voltage drop, so here the direction of voltage drop is from 1 to 2, but the current goes from 2 to 1. In this case, we should have a negative sign in the equation for the Ohm's law. Again, this negative sign does not say anything about the exact values of these three variables that we have. So this V can be negative, or this I can be negative. So this negative sign only talks about the negative sign in the equation, not the specific values. So as I said, that is what is called, what is being known as the Ohm's law, which is named after George Simon Ohm, which basically established the algebraic relationship between the voltage and current of a resistor. So in SI units, resistor is measured in ohms. So the unit for the resistance is ohms, which is shown by the Greek letter omega. So anywhere that you see, let's say R equals 10 omega, that means that this resistor is 10 ohms. So these two are basically equal. So now, since we have V to be equal Ri, if we have V and R, we can simply use this equation to find the value for I. V equals R multiplied by I, which means that I equals V divided by R. So let's say if we have the voltage to be 10 volts and the resistance to be 2 ohms, the value for I is going to be 10 volts divided by 2 ohms, which equals 5 amps. Very straightforward and very simple. So if you saw in the previous equation, we had I equals V divided by R. So there is another way of writing this equation in which we have 1 over R separated and then multiplied by V. So the reciprocal of the resistance is what is called the conductance. So the definition is in the name. If you have high resistance, that means you have low conductance. If you have low resistance, that means you have high conductance. So the relationship between conductance and resistance is complete opposite. So the conductance is shown with letter G and is measured in Siemens, which is shown with S here. So G equals 1 over R and the unit is S, which represents Siemens. So if we have, for example, a 4 ohm resistor, that means that we have a 0.25 Siemens conductor. If we have a 5 Siemens conductor, that means that we have 1 over 5 or 0.2 ohm resistor, right? There are other names for the conductance too. Another name commonly used is called mho, which is ohm spelled backward. And there is also another symbol that shows conductance that you may find in some other books. It is an inverted omega. So for ohm, we use the omega itself. For conductance, we use an inverted omega. So all of these are valid names and symbols. So now that we saw this based on the Ohm's law, what is the equation for the power consumption for a basic resistor? So if you remember from a previous video, we said that the power at any given time equals voltage at that time multiplied by the current at that time. So P equals VI, and that is true for any element in an electric circuit. So that is the first approach to calculate the power consumed by a resistor. What if you don't have the value for the voltage? but you have the value for the resistor and also the current that goes through the resistor. In that case, you can simply use Ohm's law to write V to be IR. Basically, V is IR, so you replace V with IR. And if you do that, you get a second approach to calculate the power. So in the first approach, P equals VI. So that is true no matter what is the element. It can be a conductor, it can be an inductor, it can be a capacitor, it can be a voltage source, so that is true always, right? When it comes to resistors, since we have this very simple relationship based on the Ohm's law, we can replace V with IR, and this gives us this equation, I squared multiplied by R. So that is the second approach in terms of the resistor's current to find out the power that is being consumed by a resistor. A third approach is to replace the current with its equivalent equation. So based on Ohm's law, we know that I equals V over R. So again, this is based on Ohm's law. You know, V equals Ri. So that means that I equals V over R. So if we do that, we get to the third approach that we can use to find the power that is being consumed by a resistor. So the power is going to be V squared over R. So in these two equations, we use the resistor's current and the resistor value itself to come up with equations to calculate power. What if we want to write these equations in terms of conductance? It is easy. If you remember before, we had this relationship. R would be equal to 1 over G, resistance equals 1 over conductance, which makes G being equal to 1 over R. So these two equations are completely equal. So anywhere in these equations, if you replace R with 1 over G, you can find equations for calculating the power consumed by a resistor based on its conductance. So in these equations, we have P equals I squared over G, which is equal V squared multiplied by G. So again, all of these equations are producing the exact same result, right? Sometimes it is a bit easier to use this one, right? But to be honest, it is not that easy, right? Because you see the difference between this and this is in replacing V with IR. But these, you can say, are shorthand versions of the general equation. And keep in mind that this general equation can be applied to any electric component. The following ones, these ones are only true for resistors, because for resistors we have the Ohm's law, which is very simple and shows the relationship between the voltage and the current for the resistor. So before I finish off this video, it is a good place for me to introduce the concept of having an ideal switch, because you will see this being used multiple times later on in this course. So an ideal switch is a switch that has two states. So generally speaking, this is the symbol that is being used for an ideal switch. Again, we have two terminals, terminal 1, terminal 2. And as you can see, and you probably have used this a million times, a switch is basically changes the state of our circuit between two states. So for example, this one, it can be pushed down. So we have a connection between the two terminals. So this is the first case in which the switch is pushed down. So between terminal 1 and terminal 2, there is a path now. Or it can be left alone, something like this, which means that there is no connection between terminal 1 and terminal 2. So that is the second case for the switch. When the switch is on, or case A, there is no resistance to current going through terminal 1 to terminal 2. So as soon as we do that, the current starts flowing, either in this direction or in this direction. That doesn't matter. The important thing is that there is no resistance. Because of that, we say that the switch is in short circuit state, or the alternative way is that we say the resistance is zero. On the other hand, when the switch is off or in position B, there is an infinite resistance to current going through this switch. If you consider again the Ohm law, you see that when R is 0, no matter what is the value for I, the voltage is going to be 0. On the other hand, if I want to show it the other way equation, if I use the alternative version, for I being equals to V over R. So in this case, if R equals infinity, in this fraction, no matter what is the value for voltage, the current is going to be always 0. So when the resistor is 0, the voltage across the two terminals becomes 0. So there is no resistance. We say that the switch is in short circuit. On the other hand, when the resistance is infinite, the current that goes through the terminals becomes 0. When the current is 0, we say that it is open circuit or an infinite resistance. So this is how we can use the Ohm's law to describe what happens for an ideal switch. At later lecture, you will see how we will use ideal switches. So in this video, you got introduced to Ohm's law. We saw what is the relationship between the voltage across the terminals of a resistor and the current that goes through the terminals. Based on that, we define the amount of resistance for a resistor. And using that, we define the concept of conductance that we said it is the reciprocal of the resistance. We also came up with the equations for calculating the power of the power that is being consumed by a resistor. So the basic equation, P was equal V multiplied by I. But since we had this Ohm's law that showed the relationship between the voltage and the current for a resistor, we were able to come up with some additional equations that represent the amount of power for a single resistor. And finally, we got introduced to ideal switches.